Hello. Am I clearly audible?
Assalamu alaikum, sir. Yes, sir.
Yeah. Okay, then we can start our today's lecture. In our last session, we have already started discussion on support vector machine. I want to continue the discussion. I think in our last class, we have derived this formula, that is the support vector machine for hard constraints. This formula. And then okay. Then we have utilized, that is Lagrangian method, to solve this problem. This is an optimization problem, okay, to find out W and B. And for that, how to form the Lagrangian equation, and from that equation, we want to form the dual problem, okay, so to make it dual. So this is a primal problem. Primal. From primal to make it dual, we have already taken the derivative of this one with respect to B and with respect to W, and then we got W and B equal, okay, these values, and then we have put those values in decision boundary, positive quarter, negative quarter, and then we got those new values of our decision boundary, positive quarter, negative quarter, and margin also. Then we discussed about one of the example we have already solved. This is considering our support vectors, and then we have determined our hyperplane, okay, the W transpose X plus B, the equation, hyperplane equation, considering these support vectors. So already we have discussed those in our last class. So today I want to start discussion on nonlinear support vector machine. Okay? Nonlinear support vector machine. And for that, I think we have to start from nonlinear example. Nonlinear example. Okay. Okay, please give me 2 more minutes. I will be back just after 2 minutes. So in our today's lecture, we want to discuss about the nonlinear support vector machine. Okay? Nonlinear support vector machine. So at first, we need to understand the nonlinearity in support vector machine. Let's say, if we think about a data set, the data set is given. Like a data set consists of maybe few positives and few negatives. And few negatives. Okay, then if we just if we can separate the positives from the negatives using any linear equation, okay, linear equation like a line. Okay, so you can see uh, we can separate this one. We can separate the positives from the negatives utilizing just a line. Okay, there is a line for two-dimensional case, plane for three-dimensional case, and maybe for more dimensional case, we can draw the hyperplane, and that one is also linear. Okay, there is W transpose x plus b, the hyperplane equation. So then, if the data set we have and that the instances of the data set has some positive class and negative class, and then we just utilize the linear equation to separate from from positives to negatives. Okay, so that kind of problem usually we call linear problem. That means we can utilize the linear equation to draw the separate. But sometimes the problem is non-linear. That means just only a single line, or we can say, yeah, single line or hyperplane is not enough to separate positive from the negatives. Okay? So if you can think about a problem is given, the positive is here and negative is there. So if the data set looks like this, so that means we can see that just only a single line or any linear hyperplane is not enough to separate positives from the negatives. Okay, we cannot if we draw the like this one, this line, so we can see a few misclassifications are there. That means we cannot separate positives from the negatives completely. If we want to, maybe if we try to draw uh, another, maybe this one, and then again we can see it's also not clearly separate positives from the negatives. Okay, so that means we cannot get any linear hyperplane that can maybe separate positives from the negative. Then what usually we do in case of machine learning to solve these kind of problems? Usually we draw some kind of polynomials. Okay, like this is one of the polynomial. This polynomial separate positives from the negatives. Okay, so this side of the polynomial is positive, and this side of the polynomial is negative. So this kind of polynomials usually you draw in many cases, in many regression and supervision problem. Okay, regression and classification problem. Like you can apply the polynomial regression, or maybe think about extreme gradient boosting. So those usually draw several polynomials or maybe several line segments for the regression or maybe for the classification purpose. But the problem in SVM support vector machine, it will think this problem a little bit different dimension. It will not draw the polynomials, non-linear polynomials. It will not draw that. So what it will do, it will try to translate or transform the data points in high dimensional space or maybe in other dimensional space. And after that, it will try to apply again the linear support vector machine. So that means instead of drawing just polynomials, what it will do, it will try to transform the data points in high dimensional space, or we can say in other dimensional space. And on that new dimensional space, we can use the linear support vector machine to classify positives from the negatives. Okay, so that's the different the support vector machine we have with respect to other machine learning algorithms in case of dealing with non-linear data. Okay, then think about this example. In this example, we can see that if we consider we have the positives and negatives, let's say our red squares are positive, so this is the positive, and let's say this is A. This is A, it is positive, and this is B, this is also positive. This is C, positive, and D is also positive. Okay, so these 4 instances are positive class instances. And we have, there is the P and Q, and then R, and then S. Those are our negative class instances. Okay, we can see that is the blue circles. Those are our negative class instances. So now A is positive class instance, and what's the vector for that? The vector for that is, for this is in y-axis. Okay, y-axis like x2, we have just only 2 features. One is x1 and another is x2. We can say feature x and feature y. The vector A, it will be, what's the value of x? The value of x is 0. And what's the value of y here? The y is 2. Okay, so this is the vector. How about the B? The vector B, it is, the x is 2, but y is 0. Our vector C, this is x is 0, but y is -2. And how about D? And this vector is x is -2, and y is 0. Similarly, for the P, it is x is 1 and y is also 1. And this is Q, x is 1, y is -1. And for R, this vector is -1 and negative. And S, here it is x is -1, but y is 1. Okay, so that means these are the data points we have. And now, if we want to classify or separate positives from the negatives, we want to separate positives from the negatives. That means we want to separate all our blue circles from our red squares. Then just a linear line will not be enough for that case. Okay, that means we cannot find a line like maybe this one to separate positives from the negatives. Actually, you can see that this side maybe two positives are there, but this side is also positives and negatives. So that means we cannot draw a single line to separate positives from the negatives. So how can we separate them? We can think about a circle, like we can draw a circle like this. And we can see that inside the circle, those are negative, and outside the circle, those are positive. But again, this circle is actually nonlinear equation, okay, nonlinear equation. The support vector machine will not draw such nonlinear equations, nonlinear boundaries. So that's why what it will try to do, it will try to project the data points in some higher dimensional space, or maybe the same dimensional space but in different position, or you can say different locations. So that means kind of the translation, or maybe you can say the projection or transformation we need to apply here. But for that case, different people can think it differently. For the projection function, for our translation function, or for our transformation function, people can solve the same problem differently. Okay, someone can think about, like, we want to shift our positive instances, like the red squares, maybe in right shifting. Yeah? So we want to shift all those values, all the rectangles in this side. Okay, in this side, in our right side. Someone can think about, no, we want to shift the our positive instances in upper right corner. Okay, so that means we want to shift those here like this way. So we want to find out a function that will shift those data points in upper right corner. Okay, upper right corner. Someone can think it differently. Someone can work with just only maybe the blue dots. Okay, so that's why the same problem we can solve it differently. Now think about the easiest one here. Easiest one. If we think that we want to shift the red squares in our the right side, or we can say this side. If we want to do that, then what will be the condition and how can we shift that? Specifically, we need to determine our transformation function. The transformation function, usually in SVM, it is called the kernel functions. Okay, kernel function. Sometimes we also call kernel tricks. Okay, because we need to apply some trick. That's why usually we call the kernel tricks. So this is a very simple data set, so we can apply easy tricks here. So our intention is to project the red squares in this side, okay, this right side. And we don't want to touch the blue circles. That means the blue circles will be as it is. So for that, how can we think about this? So let's say this is the B, okay, this is the point B, and we want to shift it in right side. Like, let's say in this distance. Okay, maybe we want to shift it here. Then at first we need to identify the B. Identify the B. So we can see the B. It has the B. It has the vector. In this vector, we can see two components. One is in X direction we have 2, and Y direction we have just 0. Okay, and just 0. So we can think about for this one. This one is also, you can see, -2 and 0. -2 and 0. That means we can see for these 2 points the y is 0. So can we think about like this? That is, if y equals 0 for any factor with y equals 0. If y equals 0, so what we want to do? We want to increase the value of x, because if we want to shift this b to here, then we have to increase, or you have to add some offset here uh, to relocate this b to this position. Okay, so that means we can say, can we increase the x for that? If b, then can we increase this one like the previous value of x plus of, we want to extend it, maybe we can see here, um, so you can see 1, 4, 5, 6. Okay, uh, more than 6, more than 4. Okay? More than, that means okay. Maybe you consider the 6 is here, because the distance between these two points, this is 4 actually. Okay, 1, 2, 3, 4. So if we shift this d by 4, then the d will be in b's location. Okay, so that's why I want to do it little bit more shifting. So that's why x equal x plus 6. Okay, x equal x plus 6. What will be the y? As we want to shift those in the same direction, or you can say in x direction only. So no need to think about y. No need to think about y, because the y will be y. Okay, whatever the y, we can consider this one as it is. Okay. So now, according to this equation, if we want to consider b, so here is the b. B is our 2, 0. If we check the condition first, if y equals 0, yes, y equals, for this case, then x equal x plus 6. Then what will be the new location? It will be x. Previously x is what? Previously x is 2. Okay, x is 2. 2 plus 6. That means 2 plus 6 is 8. It means we will get this value as 8. And how about the y? Y will not change, because y equal y. So that means y is same, 0. So that means 8, 0. So that means b will be translated to another location. Let's say this is our b prime. This is our b prime. So the b prime, and b prime will be 8, 0. Okay, 8, 0. Okay, and then the new location of our b will be, so this is 3, then 4, maybe 5, then 6, then 7, and then 8. Maybe this is the location of b. This will be the location of b. So this is our b prime. B prime of 8, 0. Now, if we consider our another data point d, then d is -2 and 0, -2 and 0. And then check the condition. Okay, y equal 0. This is true. If y equals 0, then what we have to do? The -2 plus of 6. Okay, so x plus 6. X plus 6. And what will be the y? Y will be the y. Okay, so the new value, can consider this one is our d prime. Minus 2 plus 6 is 4 and 0. So this will be our 4, 0. So that means the d, it will be, d will be shifted to 4. So here is the 3, this is the 4. Okay, so this is the position of our d prime. Okay, so this is our d prime now. This is our d prime. That is the 4 and 0. Okay, 4 and 0. Now we have to check all other data points, but we can see none of the data points has this y equals 0. Okay, y equals 0. So out of our 4 red squares, we already shifted 2. Again, we can see that we have also another 2, that is A and C. A and C. But if we can closely observe the properties of A and C, then we can see there is their the value of x-axis is 0. Okay, x-axis is 0. So can we introduce a new condition, that is if x equals 0. Okay, then if x equals 0, then what we want to do, we want to shift this one in this direction in any position or any position. Okay, but we want to right shift the A. If we want to right shift that A, that means we need to increase the value of x again, value of x. So let's say we want to use the same increment, that is x equal x plus 6, the same increment. Do we need to change the y? As we are just want to shift in right shifting, so that means in x direction, so no need to change y, no need to change y. So y will be the y. Okay, so in such a case, what will be the value of A? The value of A in this case, originally it is 0 to 0 2. Okay, so if you apply the transformation function, then at first we need to check whether y is 0, no. Whether x is 0, yes, x is 0. And what will be the new position? On that case, we can see it will be x equals 0, then x equal x plus 6. So x plus 6 is 0 plus 6. 0 plus 6, and 2 is 2. Okay, it means we will get the A in a new location, that is 6 and 2. Okay, so 6, 2. Then we can see this is the 4, here is the 5, and here is the 6. 5, 4, 3, 4, 5, and 6. Okay, we will get our A in this new position. Let's say this is our A prime. This is our A prime. A prime, augmented value of A, it is 6, 2. Okay, 6, 2. The A is now here. Similarly, if we consider about C, the value here, the C is our, in this case, it is 0, negative 2. So 0, negative 2. Again, the first condition y equals 0, no. Then second condition, if x equals 0, yes. Then we have to utilize this translation function, that is x equal x plus 6. Okay, so x equal x plus 6. So 0 plus 6, and y is just y, so y is negative 2. So it means we will get 6 negative 2. Consider that this is our C prime. Okay, so the C here again, this is 6. Okay, 6 means this is the location, I think. This is our C prime. C prime. Okay, 6 minus 2. Okay, now we have to check the other data points like P. P is 1 and 1. So there is no x0 and y0. Similarly, Q is also 1, negative 1. So neither of the x or nor y0 here. And for R is negative 1, negative 1. And S is negative 1 and negative 1 and positive 1. So those data points will not satisfy our conditions. Okay, so that's why only the radius parts will be shifted or translated, but the other data points will remain on the same position. So now actually we can see our new locations of A, our point B, and our C, and the D. Actually, these are the positions. Okay. So now we can see that is all the negatives and all the positives are in linearly separable, because now we can draw a single just a linear equation or just a line equation to separate positives from the negatives. So that means at first we need to apply some kernel trick or kernel function for the transformation of the data points into a new dimension, or we can see in higher dimensional space. And then we can apply the support vector machine, that is the linear support vector machine for separation. But here the challenge is to design the kernel trick or kernel function. That is the challenge. As I already mentioned that the kernel trick, kernel functions, it will be based on the data set and based on that is the user, or we can say programmer, who want to design this kernel. Okay, so there are some also kernels. Those are we say benchmark kernels or standard kernels of support vector machine, the polynomial kernel, the radial basis kernel, and the sigmoid kernel. So those usually we can apply also instead of designing our kernel by ourselves. But on that case, maybe uh, we will just utilize the same kernel, same type of kernel for every type of data set. Okay, we can try different uh, different uh, kernels, but on that case, maybe no need to design. That means you don't have any credit for that. Okay, this problem actually this problem is solved in many books. The same problem. This is the example. You will see same example in different books, but their solution is little different than this one. Okay. So now you want to summarize it, summarize the kernel function. Okay, then how can you write the kernel function for that case? Okay, so your kernel function is actually is this. That is okay. So you have designed this kernel function, the phi, for x and y for any data point, that is x and y. So x and y, how you have designed it? So it will change to x plus 6, and y will not change to this factor if x equal 0 or y equal 0. So this is your trick. And otherwise, there is x and y. So that means otherwise, if x is not 0 or maybe y is not 0, then it is otherwise. Otherwise, the value will not be changed. Okay, so it will be the xy. So for the case of x0 or maybe y0 or maybe both of the 0, then we will get the x plus 6 and y. And otherwise, whatever the value the vector has, it will be the same. Okay, that is x and y. So this is our kernel trick for solving this problem. So in your book, it is mentioned that, okay, the kernel trick can be designed for this problem in this way. There is y, x, y. It will be 6 minus x plus x minus y.
Sure. देखो right. हाँ तो सुगा.
And for y, it will be 6 minus y.
हाँ pocket मारो. दादा shot হবে. আরে সেরা দাদা shot, sexy shot.
Okay, so it will be 6 minus y plus x minus y whole square. Okay, this will be the chance if the square root of x square plus y square is greater than or equal to. Else, it will be as it is. Okay, as it is, there is xy. Otherwise, so in your book, you will find that this is actually given as a kernel function. Okay, kernel trick or kernel function. Yeah, we can do that because actually utilizing these kernel functions, we will translate the red squares in upper right corner. So that means this corner. This corner. Let's say we want to utilize this one. Let's think about the data point A for this case. Data point A. For the data point A, we will get what? We will get there is A is actually A is our 0, 2. Okay, 0, 2. So at first we need to check what? We need to check the condition. That means whether square root of x square plus y square greater than equal 2 or not. So for this case, that is x is 0 and y is 2. So that means x square, so square root of x square is 0 square, y square is 2 square. It is actually 2. Okay, the square root of 0 square plus 2 square is 2. So 2, the condition is satisfied. Okay, so it that is the 2 is equal to, yes, condition is satisfied. Okay, if condition is satisfied, then we have to utilize this transformation function. Okay? This transformation function. 6 minus x So what we will get? We will get 6 minus x. So 6 minus of x. X is what? X is 0. Plus x minus of y whole square. X is 0 and y is 2. So x minus of y whole square is minus 2 whole square. And then the y will be 6 minus y. So y is what? Y is 2. Plus x minus y whole square. X minus y will be negative 2 whole square. Okay, so this will be the translation point. Okay, so that means we can see it is 6 minus 2 square is 4. So 6 minus 2 square is 4. That means 10. And y is here is 6 minus 2 is 4. 4 plus 4 is 8. Here is 8. So that means 10 and 8. 10 and 8. In x direction it will move 10 steps, and in y direction it will move 8 steps. So that means 10 steps and 8 steps. So 10 steps, that means here is the 3, then 4, 5, 6, 7, 8, 9, 10. Okay, x direction 10, y direction 8. So that means 1, 2, 3, 4, 5, 6, 7, 8. Maybe we will get that data point here. So maybe this data point will be translated to this position. Okay, this position. So this is how the other data points, that B, C, and D, it will be translated in upper right corner. Okay, and then again, after translation, we can apply the linear support vector machine. Okay, so here is the solution for that. You can see all these data points are translated here, and after that, this is the case. Then what we can do? Again, now we can apply the linear support vector machine. So, like considering our support vectors, these are the 3 support vectors. Okay, considering these 3 support vectors, and then try to find out the W transpose x plus b equals 0. So this, find out this equation. Okay, so in our last class we have already discussed about, if we know that support vectors, then how can we find out this? Okay, so if you can remember our last class. So here we can see these are our data points. So here negative support vector, 2 negative support vector, and 1 positive support vector. Considering these 3, how can we find out the hyperplane? Okay, so the same method we have to apply here for finding out that. Okay, so finally you will get this support vector, this hyperplane, considering the support vectors, these 2 and this 1. Where you will find out that value of the W is 1, 1 and B is negative 10.057. So you will find these values. So this is how the nonlinear support vector machine, by applying some kernel trick, we can deal with the nonlinear support vector machine. But sometimes what we actually want to do, we want to apply some, instead of designing the customized kernel trick, we want to apply some form of there is the benchmark kernel functions. So what are the benchmark kernel functions? Then one of the kernel function is our, we call it polynomial kernel. So kernel function, okay, let's say the kernel function we have y, and the polynomial kernel, actually it is polynomial. Okay, so that means x, y multiplication here plus of uh, r times the degree of the polynomial. So this is called the polynomial kernel. Okay, so that means if you have the data points, then on the data points you have to apply this polynomial function to transform those data points into new dimensional space. So here the few hyperparameters are there. That is the value you can set, like the value of r and value of p. So p is the degree of polynomials. Okay, that means you can think about like 2-degree polynomials, 1-degree polynomial, 3-degree polynomials, or maybe you can say 5-degree polynomials. And r is the constant. Okay, r is a constant. You can think about like the line equation, the b. Okay, so here actually how it works. Okay, we can think about our polynomial kernel. So let's say we want to apply the 2-degree polynomial. Okay? So that is p equal to, and we want to find out. We want to use the value of r equal maybe 1. Okay, let's say this is 1. This is 1. So these are our hyperparameters. So you have to tune those hyperparameters based on your data set. So let's say this is p. So we want just 2-degree polynomial and 1. So what does it mean? It means that the polynomials actually, it will transform your data into high dimensional space. Okay. So here 2-degree polynomial, that means additional 2 degree you will get. The data points will get. That means if your data set has just only one dimension, that is x, just one dimensional data, and then applying this polynomial, you will get 3-dimensional data like this. So this is kind of the polynomials. Okay. Actually, then what's the equation for this? It is x, then y plus 1, xy plus 1, and degree is 2. So we can say actually it is our a plus b whole square. Okay, so a square plus xy plus b square. Okay, so b square is our. Okay, so can we write this one as a vector of 2 elements? Okay. For that case, if we consider this a vector that is x, rewrite is a little bit different way. Mm, 2xy plus x square y square plus 1. Then we write it like square root 2 and x, and then x square, and then 1. This one vector, and another vector can be square root of root 2y. Okay, root 2y, then y square and 1. Actually, we can write this equation in vector form of the multiplication of these two vectors. Okay, so that means we can see here root 2x, here is root 2y. So if we multiply these two, then we will get root 2 times, so root 2x times root 2y. So what we will get? 2xy, okay, 2xy. So this is our 2xy. And here is x square, here is y square. So we will get the plus x square y square. And here is 1, here is 1. 1 times 1 is 1. Okay, 1 times 1 is 1. So that means we can see that the data points we have utilizing our polynomial kernel of degree 2, we can represent it the vectors like this, these vectors, where in x direction of this vector, whatever the x value, we have to multiply that one by root 2. But in y, in another dimension, we have to consider the square of that, okay, square of x. And in third dimension, it will be just 1. So this is the constant one, the constant one. So here is also the same, root 2y, and then y square and 1. Okay. So let's say a data set is given, the one-dimensional data set. Just one-dimensional data set. Okay. For that, maybe the data points that this is these are the data points. Okay? And then these are the data points. Okay, so in this case, maybe those have some value, like here, this one is 1, this is 1, this is, sorry, this is 1, this is 2, and this is 3, but this is 4, 5, and 6, and 7, and maybe this one is 9, and then 10, then 11, like this. Okay, so we can see that this is also non-linear problem, because we cannot separate positives from the negatives just utilizing just one line here. Okay, think about the red circles are the positive and our pink circles are the negative. Okay, so how can we draw just maybe one line to separate positives from the negative? This is not possible. Okay, so actually what we need, we need to draw this kind of polynomials. But as we know that our support vector machine, actually it will not draw such kind of polynomials. So what it will try to do, it will try to transform these data points into a new dimensional space. Let's say utilizing our polynomials. Okay, so the polynomial kernel. So utilizing our polynomial kernel. So if we utilize the polynomial kernel, then here the 2-degree for the 2-degree polynomials, we can considering the p equal 2 and r equal 1. then this will be the transformation. Okay, this will be the transformation. Let's say for our that is red circles, what will be the transformation for that? In this case, we can see those are just one-dimensional data, 1, 2, 3, 4, 5, 6, like this, one-dimensional data. So what we will get after this transformation, we can see we have the x direction, it will be square root of x, and in y direction, the value will be squared, and in z direction, the value will be constant, just 1. Okay, just 1. Actually, we will get okay, what we will get. So we will get the 3-dimensional data. Now, not only the x direction, this is the x direction, this is x, and this is the y. And we have to consider also the g. And we know that the g is 1 here, always 1. Okay, so always 1. So kind of the constant, this one. So no change based on the x and y. So we can, this is constant. So we can consider that like this is just x and y we have. X and y we have. Then it means after transformation, what will be the position of this point? What will be the position of this point? Let's say this data point, this is our A. The name of this data point is A. And this is our B. So what will be the position of A, B, C, like each and every data point after this transformation, utilizing our polynomial count of degree 2. So you can say according to this, in x direction, we have to multiply each and every value by a square root of 2. So that means if in our case, this is the value, the data point, and value of the data point is 1, then what will be in x direction? So for the previous point, previous data point, that is 1, the polynomial kernel, polynomial kernel in x direction, what will be the change? In x direction, it will be the value of x, the previously it is 1, so then we have to multiply this one by root 2, so root 2 times 1. Okay, this will be in x direction. So root 2 times 1, then what will be in y direction? In y direction, it will be x square. So that means in y direction, it will be 1 square. 1 square. And what will be in z direction? It is 1. It will be 1, the constant one. So the constant one, that's why this is one-dimensional data. So from one-dimensional, we will get this 3-dimension where the z dimension or z dimension is constant. So we can see it will change in 2 dimensions. So that means this data point 1, it will shifted in x direction. The shifting will be root 2. Okay, root 2 is 1.414. So if we consider that this is 1, that 1.414 is nearly this point. Okay, nearly this
স্যার
point.
আপনার ডিসপ্লে রাইট সাইডের পোর্শনটা দেখা যায় না ফুল
দেখা যায় না? ওকে,
স্যার নিচে টাস্ক বারের আপনার টাইমের আগ পর্যন্ত দেখা যায়, তারপর একটুকার রাইট সাইডে দেখা যায় না।
ওকে, I think you can see it now.
জি স্যার এখন ঠিক আছে।
Okay, then okay, in x direction it will be root 2 times 1. So root 2 times 1 is root 2 is 1.414. 414 times 1 is 1. It is 1.414. Okay? So that is this is our 1, but now it will be shifted in x direction 1.414. So that means this will be the position in x direction. But it will be converted to a higher dimensional space. So that's why not only x, we have to consider the y also. In y direction, this is 1 square. Okay, 1 square is 1. So let's say this is our 1, this is 2, this is 3, 4, 5, 6, 7, like this. Okay, so 1, 2, 3, 4, 5, 6, 7. Now in y direction it will be 1, so that means the 1 is here. So the data point previously in this position, it will be here now. Okay, the new position of our data point will be, new position of the data point will be here. Okay, so this will be our first data point, that is the A. This is the new position of our A. Okay, so this is our A. Let's say this is kind of A prime. Okay, after transformational augmentation. And then how about the B? The B is 2. Okay, so we have to again, previously it was 2, but now we have to think about the transformation utilizing this one, square root of 2x. So square root of 2, this is square root of 2. X is what? Now the x is 2. So that means 2 root 2. We will get 2 root 2. Then what will be the transformation in y direction? It is x square. So x is 2 square, that means 4. And g axis, it will be just, okay. So this one will be the new vector, 2 root 2, then 4 plus 1. So 2 root 2, that means if root 2 is 1.414, if we multiply it by 2, then we will get 2.818. So in x direction, we will get this point. We will get this point here. Okay, we will get the point here, x direction. But how about y direction? Y direction is 4. That this data point, we will find it in this position. Okay, so this is the position. So that means okay, the B will be in this location. B will be in this location. So consider this one is our B prime. Okay, so that means we can see that is the previously it was one dimension, but now it is higher dimensional data. Like A is translated to a new position with higher dimension, B is translated to a new position with higher dimension. In this way, each and every data point will be translated to a higher dimensional space. And then maybe you will you can apply the linear support vector machine. Okay? Like a data point here, it is mentioned. You can see for this data for this case, initially this is our data point. These are our data point. Okay? These are our data point, and actually again this is, we can say, not linearly separable. So if we apply the polynomial kernel, then we will get the data points like this way. Okay, polynomial kernel, considering the R equal here is half, and our degree of polynomial equal to, you will get the data points like this way. And we can see actually now it's possible to apply the linear support vector, linear SVM, because this is the line and it will classify the positives from the negative. So this is one of the data set where we have applied the polynomial kernel for separation of positives from the negatives. Okay. So I think you understand the philosophy, that is how we can translate the data points utilizing the polynomial kernel. So there are several other types of kernels also. The equation is different. The, the hyperparameters are different also. So among them, one of the popular kernel is our called radial basis function, or BF kernel. So actually the kernel is X, Y. For the radial basis kernel, it is e to the power exp x minus y whole square by 2 sigmas. Oh, that negative. Negatives. I think so. This will be our radial basis function. So that means for that case, uh, the radial basis function can project your data in infinite dimension, kind of uh, exponential, okay, exp negative x minus y whole square by 2 sigma square. I think you can here in this as this one, okay, this one x minus 1 whole square divided by 2 sigmas. This sigma is the variance of our data set. And also we have the sigmoid kernels here, the tan as our activation function. Okay, activation function. We have k and del; those are our hyperparameters. Okay, so that means utilizing these functions, we can transform the data points into a new location or in higher dimension, and then after that, you can apply the support vector machine, linear support vector machine. Okay, so that's from our nonlinear support vector machine. Okay? Now, the last thing we want to discuss in support vector machine is uh, we call it the support vector machine with soft constraints. Okay, soft constraints, because in our last class I have discussed about the support vector machine with hard constraints and then derive it. So this one, support vector machine with hard constraints. And till now, we are just considering all forms of support vector machine with hard constraints. Okay? But there are some limitation of hard constraints. So the limitation, at first we need to understand the limitation of the support vector machine with hard constraints. Again, we want to draw our data set. Okay, let's say if we can consider our data set. Okay, the data points here, think about the one-dimensional data we have. So let's say, again, the same problem, that is the whether the individual has the obesity or not, okay. So let's say this one is the 40 kilogram. The weight of this person is 40 kilogram, and this one is 45 kilogram, and this one is 50 kilogram, and this one is 65 kilogram, and this one has 70 kilogram, and 75, 80, and 85 kilogram of it. And we can see that these people, those are just overweight people, okay. So we can say that those are the obese people. Those are our obese people. So obese people, that means the positive, okay. They have the obesity. Yes, they have the obesity. Um, uh, but we can see our these people, these individuals, they don't have the obesity, okay. So let's say they are in negative class, okay. So if you want to apply our support vector machine, then it will try to find out the support vectors first. So from our discussion from the first day of support vector machine lecture, um, to find out the support vector machine and find out the threshold, what we will do, we will find out a threshold, and we need to define that this one is one of the support vector, because the class is negative, and another support vector is this one. So this is the from the positive class, and the threshold will be at the middle position, okay, at the middle position. The threshold will be 65 plus 70 divided by 2. So it is 67.5. The threshold will be 67.5. Okay. So that means this is the threshold, and the threshold is 67.5. Now consider a test case. Okay, a test case. Consider a test case. So let's say a test case is here. Okay, so the data point we will get here. So this is a test case. Okay, test case. We want to define the class level of this test case. The class level of this test case. We want to determine the class level. So according to our threshold, it is 67.5. Let's say the test case, this one is the weight of this one is 63. Test instance, the weight of the test instance, it is the 63. So as the 63 is below our threshold, that is 67.5. So according to our threshold, the model will return that this is actually a patient with no obesity. There is a negative. Okay, so it will return the result as negative, patient with no obesity. But now we have to interpret the result. Okay, interpret the result. So if we want to interpret the result, then apply. Okay, maybe interpret the result based on our K nearest neighbor. Think about the K nearest neighbor. So KNN. So if we consider the value of K equal 1, then we can see the nearest neighbor is 65. The nearest to 63 is 65. The nearest to 63, and that one is negative. Okay, so that is the our red rectangle. Okay, so that means that negative. The patient has no obesity. So according to the KNN, where K equal 1, so we can see that the nearest people, the weight of the nearest people is actually from no obesity group. Okay, no obesity group. So that's why, okay, we can say that, okay, our patient has also no obesity. The test patient has also no obesity. But how about K equal 2? Consider the K equal 2. So if we consider the K equal 2, then what we will get? It will get another patient, another individual. But now we can see there is the one individual is positive, another one individual is negative. So that is in case of the KNN, where considering the K equal 2, we can see one patient is positive, one patient is negative. Okay. On that case, again, it's the tie. So that means we can think about weighted KNN on that case. But let's say it is 50% possibility that the patient has the obesity and 50% possibility that the patient has no obesity. So what we have to do, we have to increase the value of K. Now think about K equals 3. Now we can see that is if we try to find out the next one, then it will find out this one. So that means on that case, we can see there is the 2 will be positives and 1 will be negative. So if we consider the nearest neighbor, according to the nearest neighbor, 2 of the neighbor has the obesity and 1 of the neighbor just have, so one of the neighbor has the obesity, okay, actually no obesity. So one just, if we consider this neighbor, this neighbor, he has no obesity, okay, but another 2 neighbors, this one and this one, they have the obesity, okay, they have the obesity. So now according to KNN, where K, the value of K is 3, we have to say that actually the test case should not be there is the no obese group. It should be in obese group. Okay, it should be in obese group. So if you consider more K, then maybe it will find out this one. Okay, this one like this way. Okay, so that means the problem in explanation. That means we cannot explain without K equal 1. Okay, for the K equal 1 is fine, but for the more K, the explanation will be reversed. Okay, so that's why this is problematic. Okay, this is problematic. That means you can say most of the neighbors are positive, but based on just only one neighbor, we can say that is the negative. This is not intuitive. This is not intuitive. So that's why we cannot explain the answer of our model. So this is problematic. Okay, this is problematic. So how can we solve this problem? How can we solve this problem? Specifically, sometimes the data we usually deal with, those data also has some problem like the outliers. Sometimes the data has some outliers also. Okay, outliers also. So if we consider those outliers and then place our hyperplane based on those outliers, then In training case, maybe you will get the higher accuracy, but in testing case, you will get lower accuracy. Okay. So actually, here we can see there is this data point. This data point is kind of the outlier. Okay, kind of the outlier here, because most of the users are here. They don't have the obesity, but one of the person is here, but we can see still we are saying that he has no obesity. So it's kind of the outlier. Okay. So in support vector machine, what it will do actually, it will deal with the outliers a different way, a little bit different way. Okay. So it will not remove the outlier, but what it will do in training time, it will allow few misclassifications. In training time, it will allow few misclassifications. Let's say if we allow just one misclassification here to design the threshold. Okay? To design the threshold, if we consider that we will allow one misclassification, it means if we allow one misclassification, then this one will not be considered as our support vector. The support vector will be considered. This one will be considered as a support vector, and another support vector is this. Okay, so that means the threshold will be determined based on the 50 plus 70 divided by 2. In this case, it is 60. Okay, so then it will be 60. Okay, so that means the threshold will be here. So this one will be the threshold. 60 will be the threshold. So if the 60 will be the threshold, that means in case of the training time, so this actually, this one will be classified on training time. But now we can see the test case. If we consider now the test case, it is actually positive now. And we can explain this one based on any kind of explanation, like here, KNN. Okay, KNN is neighbor. That means most of the neighbors of these data points are positive. That's why he's also in positive. The support vector machine allow the misclassification. Okay, allow the misclassification. So this is one of the case why we need the misclassification. Okay, and in some case, even though we will try to apply some kernel functions, and utilizing those kernel functions, we want to maybe separate positives from the negatives, and then after that we want to apply there is a linear support vector machine. But in many cases, you will see that actually it's not possible to find out a kernel function. That kernel function can transform data points in such a way so that all the positives will be one side and all the negatives will be another side. So in some cases, you will not get that kind of kernel functions. So on that case, so the SVM, you will not get the solution from the SVM. Okay, solution from the SVM, and that's why specifically if you want to design the SVM function for SVM or utilize the SVM for that kind of data set, then you need to allow few misclassifications. Okay, so this is the second case. So the first case, why we need the soft margin or soft constraints, because the first one is this case. Okay, this case, because it will allow, if we allow few misclassification, then it will be beneficiary for test cases. And another is maybe is not possible to find out any kernel trick or kernel function that can clearly separate positives from the negatives. Okay, that means so that we can apply the linear support vector machine. Any question?
Sir, the
Any
screen is not visible, sir.
okay. That's no problem. I think now it's visible.
Yes, sir.
Okay, then we can continue our discussion. So now our target is to find out a support vector machine objective function considering the soft constant. That means considering some of our allowing some misclassifications. Okay, so that we can allow some misclassifications. So this is the equation. I think everyone understand this equation. Okay, so that means last class we have discussed it, but now we want to allow few misclassification. That is few misclassification. Few, the word few is there. So for that, this function we can rewrite as minimization, or we can say argument min, like argument min, the minimization what over W. The objective function, it is half, and our W, that is the Euclidean norm, the square of that. Okay. And then what we have to do, plus. So not only our, that is the maximizing the margin or the minimizing the W here. We want to do a little more. That is, we want to allow few misclassification. We want to allow few misclassification. That means plus number of misclassifications. Number of misclassifications. And for each and every misclassification, actually, we want to add a penalty for that. The penalty term is C. The penalty term is C. That means for one misclassification, we will penalize the function, the penalize it by C. Okay. So the number of misclassifications, and here we can see that this is here the minimization. That means we want to minimize the misclassification, number of misclassification. And this one we can write a little bit different way. That is, here is the argument or minimization view. The half W square. Okay. Plus of C. C is the penalty times for each and every data point. We want to introduce a slack variable. The value of the slack variable is I for all the data point. All the data point. That is for I equal 1 to n. For all the data point. For all the data point, it means if it is correctly recognized, then there will be no penalty, and otherwise we will have the penalty for that. Okay? Penalty for that. So here is the C plus C times this one. So this is called the slack variable. Slack variable. And then what is slack variable? So now in our problem we want to allow few misclassifications. Okay, let's say after allowing few misclassification, we got this hyperplane. So we got this hyperplane. Okay, and maybe we considered our there is the margin is here. And another support vector. We consider this one. So this is another support vector we considered. Okay, so maybe considering these two support vectors. Now for the data points, we can see if we consider the A, this is our data point A. This is B, this is C, and this is D. And for negative data points, we can see this is P, this is our Q, there is the R, and this is S, negative data points. Okay, few positive and few negative data points we have. And now we can see that this is the hyperplane. This is a hyperplane. And above the hyperplane is positive and below the hyperplane is negative. If we consider this, then A, B, and C, those are actually correctly identified as our positives. Okay, as our positives. But D, we can see this D. We can see that actually the D is below our hyperplane, below our hyperplane. So this one is misclassified. This one is misclassified in training time. Okay, so in training time, this one misclassified. Now for the misclassification, what we will do, we will add the penalty, or we will add the slack for that. So what will be the slack? It will be the length from our positive gutter to our, that is the D, that is positive misclassification. Okay? So for the positive misclassification, we want to compute maybe the length from the positive gutter to that. So that is from here, to this distance. This is our slack for D. Okay, slack for D. Similarly, we have another data point like this S, and we can see there is below the hyperplane. Below the hyperplane, all these are just negative, and yes, P is correctly classified, Q is correctly classified, R is also correctly classified, but S is misclassified. Okay, S is misclassified. So this S is misclassified. So then the value of the slack will be from the negative gutter to our that is negative misclassified instance. So it will be this distance. Okay, so we can consider this one as our S. Okay? So that is our slack. Okay, now we want to rewrite it. Okay, so here minimization of what? C times this one, okay, for each and every data point. Now what we have to do, uh, 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 okay. Then for the correct classification, like here we can see uh, for A, right? Here is the A. Then we can see there is for misclassified instances only we are calculating the slack variable values, okay, from opposite hyperplane. But in this case, we can see this is for correct classification. Actually, this is not opposite, okay. So that's why from hyperplane to our positive data points, the hyperplane to positive data points, this is not opposite. So that's why um, we will not get uh, there is the slack values for that, okay. So it will be like 0. So that's why we can see from here for each and every data point, sometimes we will get the slack value 0 and sometimes we will get the slack values specifically when those are misclassified, okay. Those are misclassified. Now what we have to change in our constraint, we will change it like this way, such that here is our for each and every value I equal 1 to n, that means yi, and then w transpose xi plus of b. This one greater than equal 1. Previously it was this greater than 1, but now after adding the slack values, what we have to do, we have to subtract the slack here. We have to subtract. Okay, we have to subtract the slack. It is minus the variable of our slack values. Okay, so here is I. So then the objective function will be this one. Okay, so our support vector machine optimization problem will be this one. Okay. So in this case, we can see that is the slack value. We must subtract the slack value. Then why we need to subtract it? So if you can remember that actually this part of this condition or constraint, so yi times w transpose xi plus b is greater than 1. So that means we will get the positive value for the correct classification. So positive value means if we consider the yi is our maybe we can say the positive, yi is positive, and w transpose xi plus b, that is this is also positive, then we will get the positive, okay, positive, and that's why we can see greater than equal 1. But now for the misclassifications, we are allowing few misclassifications, or few misclassifications by adding this one, that is slack. So on that case, maybe consider just one misclassified instance. So misclassified instance means yi, maybe you can say this positive, like for this d, for this d, for this d. So what we will get for the point d? This is actually original class level is 1. Okay, so this is yi will be 1. There is yd is 1. But w transpose xi plus b, this one will provide us a negative because it is below the hyperplane. Okay, so it will be negative. So it will return negative. So if this one is return negative, let's say the negative, it will return -3. It will return -3. So now, if we only consider this greater than equal 1, is it true? No, it's false. Like it's -3 greater than 1? No, it's false. But we want to allow it. We want to allow this misclassification. So what we have to do, we have to subtract this slack I, okay? Slack for D. We have to subtract the slack for D. Then what will be the slack for D? If we consider the distance, okay? So specifically we can see this distance, this distance. This is just 1, okay? And this distance is 1. So that means we can, why? Because I think already we have seen the equation of our girder, positive girder. That is, if this one is 0, then this one is 1 and this one is -1. Okay. So considering this, we can see this is just 1. Okay, this is just 1. Actually, after normalizing that, so this is 1. But from that, from our hyperplane to D, what's the distance? The distance is -3. Okay, the distance is 3 actually. Okay. Here we assume that this is 3, -3. Okay, -3. So actually we can see that the total distance of our slack, it will be 1 and here is 3, total 4. Okay, it will be total 4. So that means so the slack of D will be 4. Slack will be 4. And now we can see here it is -3 greater than or equal 1 minus 4 is -3. Okay, so that means we are allowing that misclassification. So this condition now is allowing that misclassification. Okay, allowing that misclassification. But after allowing this misclassification, we are adding the penalty for that. Okay, for one misclassification, we will get this penalty. This penalty. Okay, the C times the distance. Okay, C times the distance. Actually, here is something more to say. Not all misclassification are the same. Okay, if we allow a misclassification that are very far from our that is the borderline, that kind of misclassification is not as the same as maybe just misclassification that is nearly within the boundary. Okay, so if we allow a misclassification of long distance, so that means that as we can we already know that the distance is proportional to the confidence. Okay, confidence. But we are allowing a misclassification, long distance misclassification, that kind of misclassification, and the misclassification within the boundary. This is not the same. So that's why those are maybe misclassified within using the length is higher. Their penalty will be high, also be higher. That is, here is the distance. If we consider here our slack variable value is 4, then it will be 4c. Okay, it will be the 4c. So that 4 times the penalty usually for lower distance misclassified instances. Okay, so this is our equation. Okay, this is our equation. Now what we have to do? So this is we can say, okay, this is our problem of SVM with soft margin. This is the SVM with soft margin. And why it is called soft margin? Soft margin. Okay, or sometimes we also call this one the SVM in natural form. Specifically on that case, we use the Hind's laws. Okay, instead of slack variables, we use the Hind's laws. So this is SVM with soft margin. Why soft margin? Because we can see that is the margin we drawn here. This is the margin. So this is actually the margin, and this margin actually not clearly separate positives from the negatives. It will allow some misclassification. That's why it is soft. Okay, it is not hard. That is, all the positives will be in one side, all the negatives will be on another side. So now the next thing is how to solve this problem, that is optimization problem. So again, to solve this optimization problem, we can apply the Lagrangian method. Okay, so this is kind of the primal problem we have. We need to make it dual and then use those values in our original equation to solve. So I think this is our optimization method, Lagrangian optimization. You have already know this, how to do that. Then here's the solution. Okay, for the primal problem, we have to minimize this. Okay, that is half W square plus C summation of xi I. Okay, so this is considering this on its slack variable. They are subject to the constraints here. We can see there is yi W transpose xi plus b greater than 1 minus of sigma I. That is the xi I, and we know that the value of xi I must be greater than or equal 0. Okay, greater than or equal 0. That means so these are our constraints. So now this is objective function and these are the constraints. So how can we solve it? Again, the method we have discussed earlier in our previous lecture, that is the Lagrangian method. So we have to apply the Lagrangian. At first, form the Lagrangian equation, and then after forming the Lagrangian equation, that is, take the derivative with respect to W, take the derivative with respect to xi I, and take the derivative with respect to B. Okay, so then we will get these equations. Okay, this kind of equations we will get. The equations we will get, and then what we have to do, we have to put those equations values where in our original equation. So that means at first Lagrangian equation solve the derivative, and then after getting there, we have to put those variable values here, and decision boundary, positive quarter, negative quarter, okay, and the margin. And then utilizing those equation values, you can solve the problems like this kind of problems. Okay, I think you can think about solving the problem considering this data set. Considering this data set, there is positive, positive, and negative something. Okay, so consider this data set and try to solve our support vector machine utilizing the soft margin. So that's all in our today's lecture. So if you have any question or queries, you can ask. Hello, do you have any question or queries?
No, sir.
Okay, thank you very much. So see you in our next class. I hope I'll conduct the in-person class in our next week. Thank you very much.
Thank you, sir. Assalamu alaikum, sir.
আসসালামু আলাইকুম স্যার
Walaikum salam.
আসসালামু
আসসালামু
আলাইকুম
আলাইকুম স্যার।
স্যার আমাদের কি রেকর্ডিংটা দেওয়া যাবে?
হ্যাঁ, রেকর্ডিং আপলোড করব।
থ্যাংক ইউ স্যার।